Well, very pleased today to mention that we've got Eric Rowell. I hope I pronounced that correctly. So over to you, Eric.
Okay, thank you very much. Yeah, it's great to give a talk in this seminar. It's been a busy semester. I haven't been able to be in all of them this year, but it's finally over, and I'm glad to be joining you. So let me start by sharing screen here and hoping it works. Okay. Yes. Okay. Very good. Yeah. So what I'd like to tell you about is some work that I did recently over the last year, really, with Paul Martin of Leeds, where we're studying charge conserving Yang-Baxter operators and trying to give a classification. So I should mention that my research is supported by the NSF of the US. And I should also mention that this particular idea was really inspired by another paper that we wrote, Paul Martin and I, with Celeste Damiani. And so, yeah, so this is the idea. We're going to talk about Yang-Baxter operators. So, of course, everyone here knows what this is. So the Yang-Baxter equation, you have an automorphism of V tensor V, some finite dimensional vector space, and you define your operators R1 and R2 by tensoring up with the identity. Then you have the Yang-Baxter equation. And just maybe the question is, right, how can we describe all solutions? And so if you just look at this from a purely kind of algebraic geometry perspective, there are n to the sixth equations in n squared unknowns. And so you might expect that it's, overdetermined, but it isn't really. There's lots of solutions and we really don't know them all. So I'll just say a few words. I think I don't need to inspire anyone here to think about them, but maybe I'll just mention that really Yang-Baxter equation kind of originated in statistical mechanics. One way to think about it is in terms of the Bragg group, which is how I prefer. And so it gives local representations of the Bragg group by tensoring up with the identity as many times as needed on each side. And this is there's a bunch of conjectures about what the images should look like. There's lots of interesting things to do here. There's another inspiration, maybe it's sort of a posteriori, I guess, is that you can think of them as being like quantum circuit simulations of topological quantum computers, assuming that it's a unitary solution, for example. Another useful thing about them is that Turayev, in a paper in, I think it's CMP from 1988, he described how to construct link and knot invariants from a solution to the Yang-Baxter equation via a procedure he calls enhancement. I think this is a really neat thing to do. I haven't seen so many people apply this, but maybe it's time we look at it again. Also, in the Hopf-algebra community, there's lots of interest in solutions to the Yang-Baxter equation. They call them braided vector spaces in that community. And one of the reasons is they're trying to construct Nichols algebras from them, in particular finite dimensional ones. And this is quite useful in some approaches to classifying pointed Hopf-algebras. So that's certainly an interest. Okay, so here's the problem to start with. Classify solutions to the Yang-Baxter equation. Okay, so this is an impossibly difficult problem at the moment. I'll tell you the status. So in '93, Hayatarinta published a few papers on this, and he was able to give a classification of solutions to the Yang-Baxter equation when V has dimension 2, so 4x4 solutions. And there are about 10 families. I'm going to mention 3 of them. These, I think, are the three most interesting ones. So there's this one that sort of has no parameters in it. And there are two that have a number of parameters in them, this one and this one. And these are particularly important because, for example, the solution to the Yang-Baxter equation that comes from the universal R matrix of UQSL2 has this form. Now, these forms really are different. You can see here, if you plug A equals B equals C into both of them, you get a special case, and they will be, they'll have different eigenvalues in particular. So they're definitely not equivalent. Okay, so anyway, there's several others. So that's the dimension 2 case. Dimension higher than 3 or higher, it's completely open. Okay, so it's been 30 years since Hierarchical did his work for dimension 2, and we still really don't know the answer or much of an inkling for dimension 3. So an alternative strategy is to look at the solutions that Hierarchical found and try to generalize them into families that sort of go up in dimension. And in this way, maybe we can fill out the story. So one example of this is this first solution I mentioned, happens to be unitary. This one has a nice generalization into all dimensions that we call Gaussian Yang-Baxter operators. And they are constructed by taking, so you start with this operator U that acts on 2 copies of an m-dimensional vector space by shifting the indices and then this scalar. And then if you kind of take a Gaussian sum of these things, so here there's a coefficient here, this will satisfy the Yang-Baxter equation. So we worked these out and studied them. This is really inspired by some work of Jones, that kind of private communication that he sent me some years ago. And so anyway, we studied these. So this is just an example of the kind of thing that maybe one could try to do this. Let me mention also that this matrix is very interesting in the quantum information community, and hence all of these are, because they're generalizations. So Kaufman and Lamonaco recognize this as the so-called Bell basis change matrix. So it's a basis change matrix from the standard basis to the Bell basis, which is important in quantum information because it's it's related to entanglement. So I won't go into the details there, but I just wanted to point out that there's lots of interesting things that one can find. So now the question is, how do we generalize solutions of this form? Okay, in other words, basically of the form, the other 2 forms that I presented. So, well, let's make up some words about it. So we're going to call these charge-conserving Yang-Baxter operators. So what does this mean? Well, you start with a vector space of dimension n with the standard basis. And just for notational convenience, we're going to denote the tensor product of EI with EJ by this sort of physics notation, this ket IJ, just for convenience. And I'm going to call V upper IJ the span of the 2 basis vectors IJ and JI. Okay. Now we'll say that an operator T on 2 copies of V is charge conserving if it preserves these spaces Vij. Okay. For all I and j. You kind of think of this Ij as being the charge, and the order shouldn't matter. Okay. Let me say a little bit more about this idea of charge conserving in a more categorical way. We won't dwell on it, but this is kind of the approach we're thinking about.
Excuse me, Eric.
Yes.
I could be equal to j as possible.
That's right. Yes, that's included. Yeah, so we can think about a category of kind of such matrices, maybe more generally. So first, you can start with talking about just, so these will be, it forms a category where these matrices are actually the morphisms in the category. And so these will be monoidal categories where the object monoid will be like the integers. So just the category of matrices, of course, we all know is a category with objects, natural numbers, and just multiplication as the tensor product in the category. And then the morphisms between A and B are just matrices of the appropriate sizes. And the tensor product of morphisms is just the Kronecker product. So that's a big category. You can restrict to the subcategory generated by some fixed natural number n. Okay. And that's an interesting category to think about. So this is kind of like, you think of it as being like you're taking your block size, the tensor sizes as being n. And then you can look at, you can restrict which morphisms we're interested in. So here we call it match n. So these are charge conserving matrices. So the idea here is a generalization of what I wrote above, is that you look at the matrices in this category, morphisms, so that if you have a non-zero entry, so here I underscore and j underscore, of course, multi-indices, if and only if there's a permutation of I that gives you j. In other words, it's just basis, a tensor product of basis vectors, but permuting the order of these things, like E1, E2, E3 could go to E3, E2, E1, for example. So those can be non-zero entries. The rest of them have to be zero. So there's no map between, say, E1, tensor E1 to E2, tensor E2, tensor E2. This isn't allowed. They have to have the same collection of things, same multi-set, really. Okay, so categorically, you can think of trying to solve this problem as looking for a monoidal functor from the category of braids, that's a monoidal category, to the category of charge conserving matrices, starting with generated by an object of size n. So these will be determined by just the image of sort of a standard braid, the usual crossing. It's a way to think about it. But we won't dwell on that one too much here. Instead, let's just look at it from a more elementary perspective. So just to show you what a charge conserving matrix for dimension 3 looks like, I've suppressed all the zeros, but this is roughly how it looks. Okay, well, exactly how it looks. So you see A11, this corresponds to the subspace V11. And then you have these 4 entries corresponding to the subspace spanned by spanned by 1, 2, and 2, 1. Okay, and then et cetera. So we do this for all sizes. So now notice the general form of a charge conserving operator can be encoded in a much simpler way than having this huge matrix. Namely, we'll just define aij for I strictly less than j to be the restriction of T to that subspace. And then the sort of diagonal entries will be just T restricted to the one-dimensional spaces of this form. Okay, and so these will be just 2 by 2 matrices. So now we can encode a charge conserving operator as just a list of n scalars, A1 through AN, and then n choose 2 times 4, of course, scalars, because each of these are 2 by 2 matrices. So we've certainly reduced the number of variables. It's not completely sparse, but it's right. It still has quite a bit of, it's not a permutation matrix in general, for example. Okay, so any questions on what I mean by a charge conserving operator? Okay, so that's the idea. So now, if you look at this, we have in 1 by 1 and in choose 2 by 2 matrices. So a very natural thing to think about is like a combinatorial encoding. And that is, we're just going to take the complete graph on n vertices and think of this as a directed simplicial complex, so just, like a tetrahedron with arrows on it. And it's labeled, so there it goes 1 through 4, for example, here for K4. And notice the arrows, you don't really need the numbers because the arrows will tell you what the numbers are. And so we're going to think of, if you start with the charge conserving operator, we're going to use it to label this graph, where the edges will be decorated by the 2 by 2 matrices, Aij, and the vertices by the 1 by 1 matrices, Ai. Okay, so we have this complete graph, and we're going to label it in this way. And so, right, so the problem we study is to classify charge-conserving Yang-Baxter operators up to symmetry. So I should say a little bit about the symmetries then. So here's a lemma that talks about the symmetries. Now, if you have a charge-conserving Yang-Baxter operator, then you can conjugate by P sigma tensor P sigma, and it will remain charge-conserving and a Yang-Baxter operator, where this has to be a permutation matrix. Interestingly also, if you just take a diagonal matrix, any diagonal matrix acting on V tensor V, and conjugate, it remains a charge-conserving Yang-Baxter operator. And then one more is that if you take the flip operator that swaps Ij with Ji, naturally one can see that this preserves charge conservation, but it also preserves the Yang-Baxter equation. And so we have a number of symmetries that we can use. Now, just a few remarks. Notice you can't go conjugating by an arbitrary Q tensor Q, where Q is a 2 by 2 matrix, because that's going to destroy charge conservation. Okay, it'll still be a Yang-Baxter operator, but it won't be charge conserving. Moreover, this X equivalence, which is conjugating by an arbitrary diagonal matrix, that does not preserve the Yang-Baxter equation in general. But if it's a charge-conserving Yang-Baxter operator, then it's okay. So it's kind of an extra symmetry that we get because of our restriction. And this flip operator is kind of global. We use it sparingly. I just wanted to mention that you won't see a whole lot of it, but it's certainly something we can think about. Okay, so let's just dive right in and look at what the n equals 2 solutions look like. So there are essentially 6 forms. Okay, so up to this conjugation by a diagonal matrix. So that's why it's so useful, is it helps us sort of push away a bunch of the parameters. We can conjugate by any diagonal matrix. So we have just the really trivial solution, just a scalar multiple of the identity, which we use the label 0. We have these ones that have this middle guy being kind of skew, it's symmetric, but it's kind of this skew diagonal, if you like. And then we have 2 other kinds, which are closely related to the solutions coming from UQSL2. And so they have these nice forms. So the point is that up to X equivalence, we can always make any 4 by 4 solution that is charge conserving of one of these 6 forms. And the point is that this entry here, there's a choice. It can be either alpha or beta in both cases. Notice the middle piece here has eigenvalues alpha and beta. And so it's definitely constrained. Okay. So the first key observation in this procedure, this idea, is that if you have a charge conserving Yang-Baxter operator, then if you restrict to certain subspaces, it remains a charge conserving Yang-Baxter operator. Namely, suppose you just take some subset of the indices 1 through n and look at the span of all of those, all of the ones whose indices come from there, and call that your V. Well, if you restrict your operator to this space, it will again be a charge conserving Yang-Baxter operator. So that's quite useful. That's not something that you usually have with regular solutions of the Yang-Baxter operator. You can't really restrict because there aren't typically invariant subspaces. So to prove this, you just use, it's just a calculation that one does from the general form of these 4x4 4x4 solutions, which of course have this form here. And so you just go through and do it. So it's just a hand computation, basically. So that's nice. We understand the 4x4s. What about if we go up? Well, if you go up into all dimensions, suddenly you have a bunch of polynomial constraints. So really an algebraic variety. And here I've displayed roughly what they look like for the case of a space of dimension 3. Now, the reason I do this is that actually, even for spaces of arbitrary dimension, the equations look exactly the same, just that the indices can be ij and k. This is really key. So first of all, I've only written a few of them. You should be able to apply your symmetry action and get more, permute these things around a little bit. But the point is, no matter what dimension you're looking at, every equation only involves at most 3 of the indices, regardless of how big a size this thing is. And so that's really useful. That's kind of what makes this even feasible. So that's this key observation. Now, let me mention here I've just displayed what happens when you apply like the permutation 1, 2. It sort of swaps these two, and then it also swaps across the diagonal, and it swaps these two. So it does quite a lot. But the point is, you get a lot more equations out of it from this. So you can what I've written down is really all you need, plus the action. Okay. So here's a theorem that makes this all work. So R is a charge conserving Yang-Baxter operator if and only if, when you restrict it to a space with 3 arbitrary but distinct indices, it remains a charge conserving Yang-Baxter operator. And so, of course, the charge conserving is for free, but when the Yang-Baxter operator is the part. So one direction of this is really obvious. If you restrict, yeah, it's going to work. But the amazing thing is that if you simply go through and you can check it for all triples, I, J, K, then that it is a charge conserving Yang-Baxter operator, then the whole thing will be. Okay. So that's really kind of remarkable that you only need to check the case of n equals 3, basically. And so now the upshot of this is that in order to understand all solutions, you just understand it for n equals 3, and then you're going to start gluing your solutions together in this sort of combinatorial way, using the complete graph simplicial complex. So to do this, we need to get a little bit of notation. So for n equals 2, this is the things that we'll be labeling the edges. We have these various 2x2 matrices labeling edges, and then of course 1x1s for the vertices. And so these are the 6 that we mentioned. And so, and this includes actually the vertex labels here. So and this includes actually the vertex labels here. So alpha and alpha, alpha beta, with some mu's here, etc. Okay. And we called this, ferromagnetic because the alphas are the same here, and anti-ferro because they're different. And then there's two forms, either they're skew upper triangular or skew lower triangular. And so those are the 6 that we have at this level. So now we're going to start putting together our edges. And the interesting thing is, so a solution will correspond to some labeled complete graph, if you like. But the constraints you can think of as living at the faces, because that's the n equals 3 part of the simplex, kind of the two-dimensional thing, determined by 3 vertices. So here I'll write down the result for dimension 3. So, but I'll write it down in this kind of notation that we've developed. So this is up to x equivalents, and I'm also allowing myself all of the symmetry because I don't need to sort of work too hard. Just look at the orbits, and that's enough. And so, well, you can see what they are. Let me recall for you, this slash here corresponds to matrices of this form. So this has this sort of, it's a monomial matrix, in fact. So it has one non-zero entry in each row and column. There's diagonal entries alpha and beta, and then the sort of skew diagonal entries in this little 2x2 are both mu. We can get that by x equivalents. And then the ones that are labeled by plus or minus correspond to these two skew upper or skew lower triangular ones. And then a 0 corresponds to just the kind of trivial diagonal solutions. So these are what's labeling the edges. So going through, solving those equations, this is the pictures that we can get. So there are exactly these 10 kind of labelings that one can have. So notice if you have, there's a few things about it. So you can have all of these slashes, so all kind of these skew diagonal things. You can have zeros and these things. Anyway, you kind of go through and you write them down. It's not super instructive to look at. But one of the things I should point out is that because I'm using the action here, I can ensure that none of the edges are this sort of skew upper or skew lower triangular. I can turn those into skew upper triangulars using my action. So these are what the faces will look like. Okay, exactly these forms, one of these 10 things. And so we can start gluing it together. So we have a situation, we don't have to worry about these minuses. So just to give a little bit of an illustration of this here. So for example, this one here. So there's a little bit of extra information here. So if you have 2 slashes, then connected to something that isn't a slash, so that this edge doesn't have a slash on it, then the corresponding 2 2x2 matrices will actually be identical. Okay, so that's a lot less parameters than one might have surmised from what I drew. And similarly, if you have like all pluses or even just 2 pluses, then the corresponding 2x2 matrix is identical for all 3 of these edges. So it isn't like completely free. They influence each other in some way. So it looks a little bit complicated, but it's manageable. But I'm going to show you how to make it like completely manageable. So these observations I just mentioned about these things being the same sometimes, etc., can be completely codified. So one of the interesting things is that if you look, you never see a single slash. That never happens. And similarly, you never see 2 zeros. You only see either 1 or 3. So that gives us some kind of combinatorial consequences. So this is exactly what this theorem says, is that on any triangle, you have either no slashes, 2 slashes, or 3 slashes. So now we've distilled this just to kind of a combinatorial problem. Similarly, on any triangle, there's either no sort of zeros, 1 or 3. There's never exactly 2. So what this means is that these slashes can be used to partition the vertices. And similarly, whenever you see a 0, it'll be part of a small complete subgraph, a clique. So that helps us be able to sort of deal with this. So just to give an example, here's a picture I've drawn of a tetrahedron. And I've left off the labels. I'm just using green for slash and pink for zeros, just to not clutter it up. So in this way, right, this vertex here can be separated off from the other 3 because the slashes help partition the vertices. So the slashes sort of push this one off. Okay. And similarly, the 2 that are connected by a 0, we can kind of put those on the same level in some way, right? So we sort of, it's in this case, it's a K2. It'll be some small complete subgraph that's all pink. So in this case, it's pretty small, but it'll be just, right, a single K2 in this case. And then the other ones that are labeled by, in this case, pluses, we sort of put down below. Okay, so like this says that this vertex is sort of here. And these ones we sort of put on the same level. So this is the idea. So this is a little bit, I understand this is a little bit sketchy. There's some things that need to be filled in, but let me at least mention the theorem, which says that up to symmetry, the sort of varieties of solutions to the charge conserving Yang-Baxter operator correspond to certain transversals. And now we can give a complete combinatorial description. They're labeled by, well, first a partition of your vertices. And to make it easier, we think of partitioning them into nations. Okay. And then within each nation, you can partition them into counties. Okay, because Paul is English, states weren't the appropriate thing, they're counties. So the counties correspond to complete graphs. And then there is an order that is respected on these, which has to do with the pluses. So a plus sort of corresponds to maybe an ordering of those counties. And then within each county, we color them all of the maybe individuals or members of that county, we color them either red or blue, so 2 colors. And this corresponds to whether they sort of the value of the 1-by-1 matrices. Are they the same as other counties or different from other counties? So here's kind of an example in the case n equals 12. So here we have one county. It's order respecting, so it always goes 1, 2, and 3. This one says that we have let's say a beta for the 1, 1, sort of the A1 entry. Then we have an alpha, say, for the 2, A2, and a beta for the third one. And then these lines here, the yellow ones that indicate sort of an ordering, mean that the matrix that labels A1, 2, so the matrix A1, 2 will be of this skew upper triangular form. And I'll go into some of these a bit more in this example, but that's kind of an idea. So basically, I and J are in distinct nations if the edge between them is labeled by this stroke or slash. I and J are in the same county if the edge between them is labeled by a 0. And then the counties themselves are linearly ordered, and each county has a common color. Okay. So we've gotten pretty far from the Yang-Baxter operator at this point, I realize. But the point is that this completely works. This gives us a recipe for constructing solutions to the Yang-Baxter equation. And moreover, we can prove that any charge-conserving solution to the Yang-Baxter equation can be put into one of these forms using the symmetries. So let's unpack an example a little bit just to see how it looks. So this example that I gave before. So in this case, we have 4 nations. Okay. For example, here we have between 2 and 3, it's an ordering. So 2 is above 3. So that's a plus, we call it. It's kind of the label. And so we get the A23 has this form. And now within each nation, we have sort of a parameter subscript that will always be the same. Within nation 1, they will all be 1s. And so here, for example, in nation 2, we have these 2 red ones. So I'm calling red are going to be the betas. And so that says that A4 and A5 are both labeled, well, they're both beta 2s. And then there's this ordering that I've written down here that 1 is less than 2 is less than 3. And so that indicates that you'll have matrices of this form. Other things that one can see. So between vertices that are in different nations, that means there's a slash between them. So that means that there is a matrix of this form that labels that corresponding edge, these sort of skew diagonal things. And then if they're in the same county, such as this, and then in nation 4, then the 2x2 matrix, A11, 12, will be just this scalar multiple of the identity. So all of the information for constructing this 12 squared by 12 squared matrix is contained in this picture. Okay. So we have some free parameters, basically two for each nation. And then between each pair of distinct nations, you have parameters like mu ij, if these are countries or nations I and j. And so this is how we unpack it. Okay, so let me just kind of give an idea of the proof. And it really comes down to finding convenient transversals. So for a given charge-conserving solution to the Yang-Baxter equation, you can first just encode it using what I've said in this way, where you might have pluses and minuses in different places. The labels can be completely out of order, but then use the symmetric group symmetry to reorder kind of the basis, really. And you can do this in such a way to force it so that it instead has the form I showed before, where this is 1, 2, 3, etc. Okay. So you can convert any solution to a transversal representative. And then to check that the transversals, so these things I've described, actually give a solution, you just look at triangles. That's all that matters. And then you go back and see if indeed each triangle satisfies the conditions. And we've written down the 10 possibilities. And so you just check, is it one of these? And you're done. Okay. So that's kind of the big idea here. We can write down any solution up to symmetries. And of course, we can use the symmetries to construct more solutions if we like, but they'll be kind of equivalent anyway. So the transversals are really what we're after. And they're just exactly kind of these graphs, like this one. Okay, so I know it's kind of a lot to absorb. Maybe it's a bit technical, but I think maybe the point is that really we have a formula or a procedure for turning any solution into a transversal by using symmetries. And any transversal, we can write down a solution which can be easily checked using our big lemma that says that all you need to do is check on triangles if it indeed satisfies the Yang-Baxter equation, basically. Okay, so it might look like, oh, yeah, so how useful is this? But in fact, it is. We can actually give quite a reasonable count on how many solutions there are, of course, up to parameter choices. So maybe the first attempt at counting brings us into some kind of interesting area of combinatorics. So if you recall, if you have a solution, then each sort of edge has a label that's either a slash, a 0, a plus, or a minus. And so we'll call a sequence of these things and choose 2 of them an admissible form if you can find A1 through AN to make this a solution. And in fact, that part's not too bad. I mean, that's easy. It's just assigning the appropriate things. The real question is whether these can appear, the appropriate sequences. And these are pretty limited. So I started to count these. And so for n equals 2, we saw already that there are 4 forms that are admissible. And they live in sort of really 3 orbits in some sense, if you use the p symmetry. For n equals 3, there are 64 possible forms, right? Just sequences of these things. Only 23 of them are admissible, and they live in kind of 6 orbits. And so the orbits don't matter too much, but we have these numbers. We start doing some counting: 4, 23, 173, 1602, 17,575. And so I'm sure all of you, if you find a sequence like this, you see if it exists, see if it's some known sequence, right? And indeed it is. It turns out that they correspond to something that maybe we would call, I don't know, mathematical sociology. I'm not sure, but they're hierarchical orderings. So what is this? Let me explain. So you have n individuals, okay? You're going to first partition them into societies, okay, sort of disparate societies. So that's just a partition. And then inside each society, you weakly order them, meaning, right, you have, some hierarchical ordering, so pecking order, if you like. And there can be people that are, it's weak ordering because there can be, maybe people that have sort of the same ranking in society. Okay, and so you can count how many such things there are on a group of n individuals, and that's exactly what this sequence is. And we can prove, in fact, that we have a bijection between our admissible forms and these hierarchical orderings, and the correspondence is exactly as you can just write it down. The slashes correspond to the partition, the zeros correspond to people that are on equal footing. The plus and the minuses exactly correspond to the actual ranking, linear ranking. So these count something that's important to us. There's an improved counting, which you can start to do. So we start looking at these graphs, these sort of nations, and we can count them. So for these pictures, I'm ignoring, so there's no partition. Each of these are individual nations. And I'm ignoring the coloring for the moment. And then I'm suppressing these sort of pink lines, which corresponded to diagonal solutions, if you like. And so you start counting them, you get 1, 2, 4, 8. And then having done that, you start to throw back in the possible colorings, where we don't distinguish between a coloring that's like, if we colored this one red or blue, those don't count as different because it's just a parameter choice. And if you throw those back in, you get 3 to the n-1 possible kind of nation forms. And so now we realize the final step to count is that all we have are multi-sets of nations. And the nation should have bicolored ordered counties, if you like. So exactly these things, but now multi-sets. And there's a combinatorial device that's meant to count these kind of things. It's called the Euler transform. And we do the Euler transform to the sequence 3 to the n-1, and we start getting these numbers. And these are exactly the number, sort of the size of these transversals. And so this goes by rank, 1, 2, 3, 4, 5 on up. And so we have exactly a count of how many solutions there are, or orbits of solutions. So we can sort of condense all this down to solving charge conserving Yang-Baxter equation, to sort of counting hierarchical orderings of unlabeled members. So there's no label here, with bicolored levels, and blue always occurs in any part. So just that gets rid of this asymmetry or the symmetry between red and blue. So that gives us a combinatorial thing. So that's the story. Let me talk a little bit about future directions. So naturally, we should ask, what link invariants do we get? Sorry about that. Silence that. We should ask, what finite dimensional Nichols algebras do we get? Are there other kind of families that we can use to study other Yang-Baxter operators? Are there similar constraints for labeled complexes where you are labeling faces now and maybe the cells are constraints kind of moving up in dimension? And are there sort of categorical connections, some of which you can find in our paper, but I think there should be more. And so let me end here by saying thank you.
Oh, thank you, Eric. That was very interesting stuff there. Are there any questions?
Eric, what do you know about unitary solutions to the Yang-Baxter equation within your category of solutions?
Yeah, so we haven't, so I should say most of them are not. Mm-hmm. So these are not ones that showed up in Heather Dye's thesis. She eliminated, in particular, these forms here precisely. Right. Let's see if I can find it. A bit slow. Sorry about that. So like these forms here. These ones are rarely unitary, except probably if alpha and beta are both plus or minus 1.
Right.
Right. Yeah. But some other ones can be, like, for example, these ones, those certainly can be unitary. But yeah, it's pretty rare. Actually, we consider this a feature and not a bug, because it seems like semi-simplicity maybe limits a lot of interesting link invariants or three manifold invariants. So yeah, we're looking forward to seeing if there's something to be gained from the fact that these are not unitary.
Mm-hmm.
Are there any other questions?
Let's see, I think Fiona has a question that she put in the chat. So can anything be said about the properties of MTCs, which give braid reps into match in? Right, so yeah, so let's see. I think they would be relatively rare because usually if you have a modular tensor category, most likely the representation of the braid group is going to be unitary. So these ones kind of won't show up. So I would say there's some category that's lying around, but it's quite likely to be a non-semi-simple category if we sort of do the standard interpretation. Yeah, I have a conjecture about Yang-Baxter operators that sort of localize the braid group representations coming from modular categories. And my claim is that they should always give essentially finite braid group images. So that's sort of one connection.
I've got a couple of questions, one from ignorance and one from naivety. So if you'll forgive me, could you explain again how you get from an oriented triangle somehow to a solution? How did that go?
Yeah.
I've lost my concentration somewhere.
Yeah, sure. So yeah, so the idea is that so each edge corresponds to one of these. So I'll show you the sort of standard form of a charge conserving operator, and this is how we do it. So okay. Right, so if you have a charge conserving operator, just generally, then the sort of 2x2 matrices corresponding to the space Vij. Yeah. That is going to be a label for an edge. Okay. And then the 1x1 matrices label the vertices. Okay. So that's just for any, it doesn't have to be a Yang-Baxter operator at all. That's just for any of these things. And now the point is that the Yang-Baxter equations give us all of these constraints, and it forces for edges to only be labeled by one of these sort of 6 possibilities. And so that's one constraint, just what the edges can even have as a label. There's 6 things, that's it. On the other hand, if you look at these equations, these then put constraints on how you can put your triangles to, build a triangle out of edges. And that is the one that gives us sort of these pictures here. So for n equals 3, they all look like this, up to the appropriate symmetries. And so that sort of gives us a constraint. And yeah, so it's just very few of them. So if I look at any of these things, I see this plus. Now it's clear that this is a 1, 2, 3. This is a plus, so that tells me that the 1, 3 edge, so A1, 3, will be a matrix of this form, for example, in this encoding. And each of the other edge labels also similarly give some information. And the slashes are the ones that give sort of these skew looking ones like this, and zeros give diagonal ones. So that's it. Yeah.
Okay, but I guess this is all described in your paper.
Yeah. Right. So yeah, there's basically an algorithm. If you give me, one of these kind of very combinatorial things, just a sequence of nations with counties and some colors on them. From those, I can write down all of the matrices, the 1 by 1, the 2 by 2 matrices, and guarantee to you that they satisfy the Yang-Baxter equation. So it can be implemented on a computer even pretty directly.
Well,
So the paper you're referring to is your paper with Paul Martin?
That's right. Yes.
Yeah. We could put that into the Dropbox along with your slides if you would like. And
sure.
if you would send me and Roger your slides.
Okay.
And
I'll do that for sure.
Well, the other question was the naive one. If you've got a set theoretic solution of the Yang-Baxter, which I like to think of as a sort of unentangled solution. And if you've got such a thing, it automatically gives you a solution with tensor products.
Yep.
So a number of these Yang-Baxter equation solutions will be either entangled or unentangled. And I guess the entangled ones are the more interesting ones. Are the solutions you come up with entangled?
what do you mean by entangled?
By entangled, I mean they don't come from a set theoretic solution.
Oh, okay. Mm-hmm.
Yes, some of them do. I think so. So there's different interpretations of entangled. But if we just look at these 2 by 2 solutions,
I mean,
right?
I may not be using the right words, but it's just
yeah. So I think ours probably are not set theoretical. So obviously we would need to set some parameters to 1 or something like this. These ones here, those might be set theoretical.
Right.
For mu and alpha and beta all 1, right? Because anything that's set theoretical is automatically, in particular, a permutation matrix.
Yeah.
And so we declare alpha plus beta should not be 0 here, for example. So these ones, the only ones here that would be, permutation matrices, even up to a scalar, up to choices of scalars, would be these 2. These ones are never set theoretical.
Right.
Yeah. On the other hand, we miss a lot of set theoretical ones as well, because you're allowed to permute kind of quite interestingly. Right. That's an arbitrary permutation of v squared things, or n squared things.
Okay. Are there any more questions?
I have a question.
Okay.
So, so thank you for the interesting talk. I have a question about, so suppose that you do have a solution, then you can decompose it into these basic types as some kind of combination of the basic types. So say for solutions coming from representations of quantum groups, is there something that can be said about the different counts of how many of these happen, or in what kind of combinations that these show up in?
Yeah, so I think that most of the solutions of the Yang-Baxter equation that come as solutions, to the universal R matrix of some quantum group, I think most of these won't show up here. I think probably only the SL2 ones show up here, or possibly, SL2, cross with itself in some ways. This might happen, but so I as far as I can tell, if you were to take, say SO3, or something like that, quantum SO3, or one of these other, maybe SO5, it wouldn't show up here. But those, in some sense, those are interesting, next step questions to address. Can those ones be generalized in sort of a similar way? Yeah.
Okay. Yeah. So this anti-diagonal one. So I have some results about the SL3 at a root of unity. So looking at that R matrix, you do get this anti-diagonal block that that looks like that, and from this non-semi-simplicity.
Okay. Yeah. In the non-semi-simple case, I see. So that's yeah. Okay, that sounds very interesting. I'd like to know more about this for sure. Send me something.
All right. Yeah, sounds good. Yeah, I'll let you know. Thank you.
Okay, well, I better end there now. So thank you again, Eric, for a very interesting talk. So thank you. And just say that I think next week it'll be Jose Montesinos, but I will check. So I hope to see you all next week. Bye for now.
Thanks.